Evening, guys. Today, or this afternoon, this evening, I'm going to talk to you about the difference between series and parallel circuits. We went over this on Wednesday in class, but I figured I'd go through it one more time, nice and quick, just to supplement what we're going to go through when we're mucking around with a bunch of wires and power supplies and stuff. So, a series circuit, parallel circuit, and a composite circuit. Series one is basically like everything is joined together like links in a chain. We have bits of electrical wire, then we have an object like a light globe, then we have more electrical wire, then we have another object like a light globe, and so on and so on. If one of those links breaks, the chain is useless, so no electricity can flow. With a parallel circuit though, we have every component kind of piggybacked or backed onto each other component. And what that means is that if one of the bits that's piggybacked on fails, so a fuse blows, the globe blows, whatever it is, the electricity still has a choice, still has options to make its way through the rest of the circuit. Composite circuit is basically a combination of the first two. This is what a series circuit actually looks like. So we have a power supply here. The electricity will go through wires, through this little thing's a globe, through another globe, and back again. So if any of these links breaks, my cat is hovering by the microphone, by the way, get out of the way, buddy. This is a series circuit, so if any of these links in the chain breaks, electricity can't go through any of the other bits and pieces. What this means is that the current that goes, so the electricity, the actual electrons that are flowing, that flow out of this side here and make their way back to the other side of the battery, have to go through everything. What that means is that the current is constant everywhere, and the voltage that the power supply can put out is shared across this globe and this globe and this globe and any other bits and pieces that are in there. With a parallel circuit, you can see this is what I mean by piggybacked on. So we have one bit there, and then the other bit is put on there, and then the other bit is put on there. Each component that you add is basically an alternative path for the electricity to flow through. What that means is that we have the same amount of voltage across each of these things, but the electrons have got a choice between going through the first globe or the second one or the third one or a switch or whatever else, diodes and resistors and all that other sort of stuff throughout the circuit. What that means is that voltage is constant, and the current is shared. So using an analogy like this stadium map of Adelaide Oval, you'll notice it's Port Adelaide from 2015. So I've put a whole bunch of tarps in the outer wing here. We have 1, 2, 3, 4 gates. If this was organised in series, what it would mean is that you would have to line up behind one of these gates, go through that, security check the whole lot, then go through the next gate, and then the next gate, and then the next gate before you actually go into the ground. What this does is slows down the flow of people getting to the ground. Adelaide's playing Richmond right now. If Hadji had to line up behind this gate and then go through this one and then go through this one and then go through this one before he got into his member seat somewhere in here, he'd be fairly teed off, I would imagine. If we organise this in parallel, which is kind of what they do anyway, that means that someone coming from this way, the riverbank stand, or someone up here, Montefiore Hill, you've got an option to go through this gate or this gate here. So that means if you're coming down the hill and you see, 5,000 people here, you go, oh, bugger that, I'll go through this one, it's a little bit easier. All right, so with the flow of electricity, it takes the path of least resistance. It's like one of you guys, when I ask you to do your work, you are taking the path of least resistance. So doing your work, is that worth it, or do I have to push you, increase the voltage, so to speak, in order to get you to do something? When we are looking at calculating the voltage or current or resistance in series and parallel circuits, what we are going to use is a thing called Ohm's Law. So Ohm was a guy who played around with a whole bunch of electricity stuff back in the day, and he discovered that the voltage through a circuit is equal to its current times by its resistance. So the voltage is the push, so the pressure in a water pipe. I is the current, is the amount of electricity, so the actual flow of water through the pipe, and R is the resistance, which is, I guess, the resistance. So how much each of the bits and pieces, the globes, I guess, resisting that flow. When we're working out the resistance for a series circuit, we end up with this. Because the current is the same everywhere, we can, so don't worry about the maths, we can rearrange it, we end up with this thing here. The total resistance is equal to each of the little bits and pieces added together. When we're looking at a parallel circuit where the current is different everywhere and the voltage is the same, we end up with this ugly piece of stuff. 1 over the total resistance is equal to 1 over the first resistor plus 1 over the second plus 1 over the third. Effectively, what you need to do is add up 1 over all of the little bits and pieces and then do the inverse or the reciprocal, or 1 over that number. So an example, we have 3 resistors and we connect them in series like this. 1, 2, 3. We add them up. Total resistance is 5, first one, plus 5, the second one, plus 5, the third one. We end up with a total of 15 ohms. So Ohms Law, we're naming after ohms. This is the Greek omega. It's kind of makes sense. If we're adding them up in parallel though, we go like this. 1 over the total resistance is 1 over 5 plus 1 over 5 plus 1 over 5. So these are the resistors. We add that all together and we get 1 over the total resistance is 3 over 5. So 1, 2, 3 over 5, which means that when we flip it upside down, the total resistance here is 5 over 3. So if we connect them in series, 15 ohms. If we connect them in parallel, 1.67 ohms, I think it is. So you can see that the resistance here is a lot higher because the electricity's got no choice but to go through everything. The resistance here is a lot lower because the electricity's got some options.